Meow. Hello, everyone. Uh, Welcome to sort of the first time I do this type of video. Um, Today I'm just going to be covering a higher level chemistry IB paper, paper 3. This is going to be primarily focused on option C, which is um, energy, I think. And this is suitable for both standard level and higher level students. So I'm sure everyone will benefit from this. And if this video is not for you, then get out. Thank you. So let's get ready with the first question. So here the question says, the sun's energy is produced by the fusion of hydrogen nuclei. Explain fusion reactions with reference to binding energy. So binding energy is basically the amount of energy required to separate like a particle from a system. So firstly, let's define fusion reactions. So fusion reactions is when smaller nuclei combine together to form a larger nuclei, and in doing so, the products should have a larger binding energy. So they should have a larger binding energy. I'm just gonna write BE because obviously it would take more energy to split apart a particle if it's larger. And oh, just quick note, you can pause the video at any time and attempt these questions yourself. Part B says uranium-238 produces plutonium-239, which is used as fuel in breeder reactors. Outline why the term breeder is used for the reactors. Well, basically, the term breeder is just a reaction where it produces more material than it consumes. So we can sort of define this as it produces more fissile material than it consumes. Fissile is just any atom or element that is able to undergo nuclear fission. So yeah, that's just a simple one marker, so we don't need to elaborate anymore. And second part of part B says deduce the fission reaction when 239 um, plutonium is bombarded with a neutron to produce xenon and zirconium. And this is pretty self-explanatory. We have 239 plutonium bombarded with a neutron, so we can just have neutron, and this reacts to produce obviously xenon and zirconium. And obviously we need to make sure that the mass number on both ends are the same. So here it equals to 240, and on the right side, if you just put it in the calculator, equals to 236. So we're actually missing 4 neutrons, so we can just add it right here, 4 neutrons, which makes this fission reaction complete. Let me just get it, the next question. So, hold on, sorry. There we go. I just paste in part C and part D. So here we have part C, which says nuclear disasters release radioactive cesium into the atmosphere, which presents serious health risks. Cesium-137 has a half-life of 30 years. Calculate the percentage of cesium-137 remaining in the atmosphere after 240 years. Okay, so first of all, we need to deduce the number of half-lives required. So this is just simple division. We can do 240 divided by 30, which is 8. So there's a total of 8 half-lives. And in order to calculate the number of, or the percentage that's remaining in the atmosphere, we can just take half to the power of the number of half-lives and then multiply that by 100 because we're dealing in terms of percentages. And that should give us, if I plug it into the calculator, 0.39%. So in total, there's 0.39% cesium-137 remaining in the atmosphere after 240 years. Part D asks us, nuclear energy produces ionizing radiation, which leads to the formation of free radicals. Deduce a Lewis structure of the superoxide O2 free radical. So we know we're going to be dealing with a double bond because of it's O2, it's diatomic. So immediately we can express this in the form of, obviously, hold on, sorry. So since it's diatomic, it's going to be undergoing a covalent bond, which means these two oxygen atoms are going to be sharing an electron. So in order to express this properly, we can, instead of writing, this would be incorrect, we write that they share one pair of electron, and then we can say that since two of them require to have a full outer shell, and they both offer eight electrons to the outside, they have to share one right here, because it wouldn't make sense to have, let's say like that, because only one of the electrons would have to go to complete both of their shells. And then obviously we can't forget the negative right here, so you can just write the brackets and the negative. Oh, there's one more question that I forgot to paste in for question 1. I'll just go ahead and paste that in right now. Explain why free radicals are harmful to living cells. Well, these sort of biological questions, you sort of have to use a broader knowledge of our abilities. This doesn't directly relate to, our chosen option in chemistry, but we can assume that living cells have to have, a good reaction, and the enzymes have to work in order, and the DNA has to be proper. So we can assume that since they're harmful to living cells, we can say that it can possibly, damage the enzymes of these cells, which in turn could possibly cause cancer. So I'll just draw an arrow, which means cause cancer. Now I'm not quite sure if this would award the 2 marks, because I haven't really delved into you know, the topic of if what's harmful and what's not. And yeah, that should be it for question 1, I think. A, B, C, D. Yep. Let's go on, moving on to question 2. Yeah. I'll just zoom out so all of the questions fit in. Yep, there we go. Alright, here's the majority of question 2. I'll just, there we go. Just to get it, oop, that's too much. Alright, so question 2. Part A says 1.57% of the mass of a rock weighing 46.5 kilograms is uranium-6 oxide, UO2. 99.28% of the uranium atoms in the rock are uranium-238. Show that the mass of uranium-238 isotope in the rock is 0.639. Right, so this is pretty confusing, so I'm just gonna break it down. So at first we need to calculate the percentage of uranium in uranium oxide. So what we have to do is we know that uranium is 238, the mass number of it, so we have 238 divided by, because it's the mass of that specific element, the formula is the mass of that specific element divided by the whole compound, right? In order to find, how much that one element makes up the percentage of the entire compound. So we'll take uranium-238, and which is 238, and then we'll take the whole compound, uranium oxide, which is 238 plus the atomic the molar mass of oxygen is 16, and there's 2 of them, so 16 times 2. And if I put that in the calculator, it should equal to 0.881, which basically means that 88.1% of this compound is made up of uranium, right? So now that we got that covered, we should take that 0.881 and multiply it by the percentage of the mass of the entire rock, right? Because we're looking at just the rock itself. We're not looking at just this compound. So we'll multiply it by that percentage of the rock. So we just divide this by 100, which is 0.0157. So now that we have the mass of the uranium isotope which is 88%, multiplied by the mass of this compound, which has the uranium in the rock, which is 1.57%, and then we multiply that with the mass of the rock, because that's the total, that's the total value of the whole thing. And we should multiply that by 0.992, because not necessarily that this compound has uranium-238 specifically, because here it says 99.28% of the uranium atoms in the rock are uranium-238, because there could be other isotopes like 239, 237 that we don't care about, so we should times it by 0.9928 to calculate the mass of specifically uranium-238. So in order to reiterate what I said, we take the percentage of uranium-238 in uranium dioxide, uranium oxide, which is this, 0.881, multiply that by the mass of the rock, which is the percentage of that uranium oxide in the rock, which is 1.57%. And then we multiply that by the mass of the rock, which is 46.5 kilograms, because we're calculating the mass of the isotope itself in the rock. And then we multiply that by the percentage that those uranium atoms are uranium-238. It sounds a bit confusing, but I've tried my best to explain it. And if we just plug all of that in the calculator, so we have 0.881 times 0.0157 times 46.5 times 0.028, we should get 0.6388, which rounds up to 0.639. See, we got that right. That's a pretty surprising question, like 2 marks. But yeah, anyways. Right, so moving on to part B. Part B says the half-life of uranium-238 is 4.47 times 10 to the power of 9 years. Calculate the mass of uranium-238 that remains after 0.638 kilograms is decayed for 2.23 times 10 to the power of 10 years. Right, okay. So, in order to calculate the half-life, we take the amount it's decayed for, and we divide that by the overall half-life. So we got 2.23 times 10 to the power of 10. I assume that says that, yeah. Divide that by 4.46 times 10 to the power of 9. If you put that in a calculator, 2.23 times 10 to the power of 10 should come out to, 5 half-lives. I'm just going to HL. 5 half-lives. And all we have to do is we take half and we raise it to the power of the half-lives, and we multiply that by the mass of the uranium that remains after it's been decayed. So we do that, and we should have around, if I put it in a calculator, should have 0.0199, which is just 0.2 kilograms of uranium-238 left after it's decayed for this long. That's a much simpler 2-marker compared to this last one. Right, so part C is sort of the same analogy as this question right here in question 1, which is outline a health risk produced by exposure to radioactive decay. Well, it's pretty good that this is just worth 1 mark, because common sense, the exposure to radioactive decay can lead to possibly genetic mutations. We can say that. Or more simply, actually, we can just say cancer. Yeah. Right. Part D says deduce the nuclear equation for the decay of uranium-238 to thorium-234. So obviously we have uranium right here, which has a mass number of 92. Or not a mass number of 92, a proton number of 92. And we have thorium 234, which has an atomic number of, if we just go to the data booklet, and you can see that thorium has an atomic number of 90. So we'll put 90 down here. And obviously, the nuclear equation for the decay of uranium-238 to thorium-234 has to be an alpha particle. So we have helium. And in order to make the mass numbers, the numbers at the top and the numbers at the bottom, to match, we can see 92 divided by 90 is 2, because there's 2 neutrons missing. And same with the top. We have 4 that's missing, so we'll have 4 up here. These are neutrons and protons. And moving on to part E, which says thorium-234 has a higher binding energy per nucleon than uranium-238. Outline what is meant by the binding energy of a nucleus. And yeah, I'm pretty sure I explained this before, so we can easily define it. So the binding energy, BE, binding energy, is the energy required to separate a nucleus. Let's get technical. We can say the energy required to separate the nucleus into protons and not electrons, neutrons, or nucleons. You can just say nucleons instead. And yeah, that should be it for this question. I think we're missing one more part though. Oh yeah, part F. I'll just copy and paste that in right now. Yep. So, here we have determine the nuclear binding energy in joules of uranium-238 using section 2 and 4 of the data booklet. So, okay. So, in order to do this, we need to use, pretty sure, Einstein's formula. We need to use E equals mc squared. So, in order to do that, I'm pretty sure, first we need to calculate the mass, the overall mass of uranium-238. So to do that, first of all, we can get obviously the atomic symbol with all the numbers of uranium-238. So we know that uranium, we'll just write out here, 238 has mass number, or not, or atomic number of 92. So in order to determine the energy, first we need to find M, which stands for mass. So we need to find the mass of all the protons and electrons and neutrons and all of that. So that's where section 2 and 4 of the data booklet come in. So I can just actually paste in section 4. Section 4 is right here. So at first, we should calculate the mass of the nucleus of uranium first, which we can see here. The mass of the nucleus is this big number right here. And at first, we need to find the value, the constant value of AMU. So this is where we use section 2 of the data booklet. So I can go ahead and paste that in right here as well. Yep. So you can see right here, using section 2 and 4 of the data booklet, 1 AMU equals 1.66 times 10 to the power of negative 27 kilograms. So at first, we should calculate the mass of the nucleus. So you can take 238.05 times 1.66 times 10 to the power of 27. Also, I recommend in your calculators to write these in brackets, just to not get anything confused. And I would also recommend writing the whole decimals, all the numbers in decimals, just in case there's trouble with rounding up. I'm just doing it now because I can't be bothered to write all of them with the mouse. And if we put this in a calculator, we should get 2.38 times. Yeah, you should get 3.95 times 10 to the power of negative 25. And now that we found the mass of the nucleus, we need to find the mass of the protons and the mass of the neutrons in order to, and we subtract that from this right here in order to get the mass of the overall mass apart from the nucleus. So instead of explaining with my words, I can just go ahead and do it. So we take this right here, which is the value of the proton and electrons, and we multiply it by, the mass of the protons, and we multiply it by the mass of each proton in section 4 of the data booklet. So we have 92 multiplied by 1.67222 times 10 to the power of negative 27, right? And yeah, and we add this with the mass of the remaining. So the remaining electrons. So to find the electrons, we take the overall mass number and we subtract it from the proton number. And 238 minus 92, we should get 146 times, and obviously we take the value of the neutrons and we multiply that with the neutron number of uranium. So 4927 times 10 to the power of negative 27. So now we have the mass of the protons and we have the mass of the neutrons. So after we have both the mass of the protons and neutrons, we should minus it with the overall mass of the nucleus, which is 3.95 times 10 to the power of negative 25. And we're doing this in order to calculate the amount of the mass number of the electrons, because we don't have the electron number, we don't know what it is. And the electrons is what really matters in nuclear binding energy, because it's the energy required to separate a nucleus into protons and neutrons, and we can't really do that if we still have electrons. So I'll just type in this massive calculation into my calculator, and I'm just gonna round up to like 3 significant figures actually. Yeah. Yeah. So in doing so, we should get the overall value of 3.42 times 10 to the power of negative 27. And now that we found m, all we need to find is c, which we basically know what c is. It's 3 times 10 to the power of 11 using section, right here, it says it right here. 3 times 10 to the power of 8. Sorry for my mistake there. And we just multiply them together. So we have 3.42 times 10 to the power of negative 27 multiplied by speed of light squared. And in doing so, we should get the energy of conservational mass, which is the nuclear binding energy, because that's how much is required in order to separate the nucleus of uranium-238, which, if I do it, should equal to 3.08 times 10 to the power of negative 10. And that should be our final answer for part F. Yeah. So I'll just load up question 3 right now. Right, so here I have question 3, I think, copied in. So here question 3 says, gasoline, biodiesel, and ethanol are fuels. And they give us a nice table showing the chemical structure and energy density of these three fuels. And part A asks us, calculate the energy released in kilojoules from the complete combustion of 5 decimeter cubed of ethanol. So immediately we know that we're dealing with ethanol only, so we can immediately cross out these two. So we can see that the energy density of 1 kilojoule decimeter cubed of ethanol is 21,200. But since we're calculating the complete combustion of 5 decimeter cubed of ethanol, we should multiply this number by 5, which should give us 106,000. Yeah, 106,000 flat, which can be written as 1.06 times 10 to the power of 5. Yeah, that's part A. And part B says, state a class of organic compounds found in gasoline. So now we know we're dealing with gasoline, so we can cross out these two. And we can see that the chemical structure of gasoline is mainly hydrocarbons of chain length C4 and C12. And these hydrocarbons are composed of either alkanes or alkenes usually. So we can just go ahead and pick one. Just go with alkanes. That should be it for part B. Let me get part C and D. Yeah, right here. Here it says, for part C, outline the advantages and disadvantages of using biodiesel instead of gasoline as fuel for a car. Exclude any discussion of cost. So immediately we should not talk about anything related to price or cost, and even if it's a slight mention of it, we shouldn't take risk, as we shouldn't risk deduction of marks. So one advantage immediately that comes up to mind for using biodiesel is the fact that it's renewable. And biodiesel, because it's, I assume, more environmentally friendly than gasoline, we can say it it has a lower carbon footprint than gasoline. And right, so, and now for the disadvantages of biodiesel instead of ethanol, is that biodiesel takes a lot more time to produce, these the plants that is used for fuel. So we can just say time consuming. And another point would be that takes up a lot of space, takes up land, which could probably cause other factors like deforestation, and it could possibly affect the biodiversity. So to sort of be general about it, we can just say takes up land. Or if we're looking to make sure we get that mark, we can go ahead and be specific and say deforestation, because probably cut down trees to have more land to grow these plants. And part D says a mixture of gasoline and ethanol is often used as a fuel, suggests an advantage of such a mixture over the use of pure gasoline. Exclude any discussion of cost. Right. So obviously, when you use a mixture instead of a pure substance, and this is to do with cars, we can say that there's less knocking in the engine, so the fuel burns more evenly, we can describe it as. So it has the correct mixture of fuel and air instead of having a pure substance, which can cause there to be sort of like an uneven reaction, and it could cause spark ignition, which is not caused from the usual spark plug. So you can just say here less knocking. And I'm pretty sure I missed out one part of that question, which, yeah, right here. I missed out this part. Right, so for part 2, here it says methane is another greenhouse gas. Contrast the reasons why methane and carbon dioxide are considered significant greenhouse gases. So we can immediately say that CO2 is much more abundant than methane in the atmosphere. Than methane in atmosphere, which could possibly make it a factor of that it contributes more to global warming. Global warming. And that's one reason right here. And the second reason, I'm pretty sure we can talk about the absorption of infrared radiation in the atmosphere. So we can say that methane absorbs more infrared radiation than carbon dioxide. And I think this is supported in section 26 of the data booklet. I can go ahead and paste it right now, right here. Here we see that methane is an alkane, which has a strong infrared radiation absorption. So we can assume that it's stronger than carbon dioxide, because obviously carbon dioxide is more abundant, therefore it could possibly be less potent, and therefore it has a lower infrared radiation absorption than methane, because obviously methane absorbs the IR radiation way more than, or stronger, or is more effective than carbon dioxide. And moving on to part 3, it says suggest a wave number absorbed by methane gas. This should be a free mark. It's given to us in the data booklet. You can just go down to the type of organic molecule methane is, which is an alkane, and we can go ahead and say basically any number between this criteria. So I'll just go with 2,869. Seems like the most mature number to put. And Part 4 here says determine the relative rate of effusion of methane, which has a molar mass of 16.05, to carbon dioxide, which has a molar mass of 44.01, under the same conditions of temperature and pressure. Use section 1 of the data booklet. So let me just go to section 1 of the data booklet. Here we can find the equation of rate of effusion. I'm pretty sure it is given to us, which is common sense right here. I'll just go ahead and paste it. And here we can see that it's the final rate over the, or MR2 over M1. So we can see it's rate 1 over rate 2. So it's CH4. It's from methane to carbon dioxide, which equals to the square root of M2, which is carbon dioxide, because this is M1, methane is M1, carbon dioxide is M2, which is 44.01, divided by 16.05. And if we just put this in a calculator, we should get 1.66, which is the relative rate of fusion. And that should be it, I assume, to question 3. Yeah. So moving on to question 4. Here, paste it right here. Here it says, an investigation was carried out to determine the effect of chain length of the alcohol on the equilibrium constant Kc for the reversible reaction. And here we have obviously the reactants in the products and the catalyst. And here it says fixed volumes of each alcohol, the ethanoic acid and the sulfuric acid catalyst, were placed in sealed conical flasks. At equilibrium, the flasks were placed in an ice bath, and samples of each flask titrated with sodium hydroxide to determine the ethanoic acid concentration present in the equilibrium mixture. So the following process results were obtained. Here we have the reactants of each alcohol. We have the chain length, the determined equilibrium constant, and the actual value of the equilibrium constant. And here part A says identify the independent and dependent variables in this experiment. So obviously the independent variable is what's changing, and here we can see that it's the number of carbons or carbon atoms in each alcohol. So we can just go ahead and say number of carbon atoms in each alcohol. And the dependent variable is basically like what you're measuring. So here we can say that we're measuring the equilibrium, or no, we're measuring the concentration of ethanoic acid present in the mixture. So you can literally just say, concentration of ethanoic acid. Here, part B says the ice bath is used at equilibrium to slow down the forward and reverse reactions. Explain why adding a large amount of water to the reaction mixture would also slow down both reactions. So obviously, if you have a ice bath with, let's say, this much water, right? And you add a large amount of water so that it fills up right here. Obviously, there would be a lower concentration of the acid catalyst used to speed up this reaction, because there is a larger body of water, which means that it would dilute at a lower concentration. And, or not dilute at a lower concentration, it would be obviously a lower concentration, therefore less dilution. So you can say, since it's 2 marks, you can say less dilution because there's less frequent collisions in the ice bath. But we don't need to say that. And let me just go ahead and paste part the rest of the question. Right, so for part C it says, suggest why the titration must be conducted quickly even though a low temperature is maintained. So let's assume that titration is conducted slowly. So if a titration is conducted slowly, that you're taking small intervals between a reaction of the titrant and the titrate, then the titrant would be added faster, at a faster rate, then it can react with the titrate, the unknown concentration, which would cause the equilibrium to shift because there would be a deferred equivalency point. So we can say here that if titrant is added faster, then it can react with titrate, then equilibrium will shift. It's a pretty self-explanatory reason. Moving on to part D. An additional experiment was conducted in which only the sulfuric acid catalyst was titrated with sodium hydroxide. Outline why this experiment is necessary. Well, here we can see that it was titrated with sodium hydroxide, which is a sort of like a strong alkaline, and in doing so it's being reacted with the catalyst of an acid. So by stabilizing sort of the pH, it helps eliminate the error that was caused by the sulfuric acid catalyst. So we can say that reduces error of acid, error caused by acid catalyst. Because of NaOH, it helps balance sort of the pH and control the experiment altogether. And part E says calculate the percentage uncertainty and percentage error in the experimentally determined value of Kc for methanol. So the difference between error and uncertainty is that uncertainty is the value that lies within a range of values, which within those range of values the true value is asserted in. So we can say that between 0.1 and 0.5 the true value is between these two restrictions. But with error, it's error is the difference between the true value and the measured value. So right here for percentage uncertainty, we can see that um, we can take methanol, so we'll ignore everything else but methanol. And we can see that the error of the measured value was 0.4, and we can times that by 100 because we're dealing with percentages, which gives us 40, and divide that by the measured value, which gives us the uncertainty of the range of which it lies in. So if we do this, I'm pretty sure this is just 6, right? Yeah. So 6, this would be 6%. Because you're taking that value that it lies in, plus or minus 4, you're timesing it by 100, which gives us the percentage, which is 40%, and you divide that by the measured value that that range lies on, which gives us the overall percentage uncertainty. And error, it's a little bit different. Error, you take the experimented value, you minus it with the actual value, and then you divide it by the experimental again. It's, I think it's a formula, it's theoretical minus actual divided by theoretical. I'm not going to write it all. So it'd be 6.5 minus 5.3 divided by 6.5. If you put that in a calculator, times it by 100, because we're dealing with percentages, we would get 23% on average. Right, and for part F, it says comment on the magnitudes of random and systematic errors in this experiment using the answers in E. So we'll start with percentage uncertainty. We can see that's pretty low. So we can say that a small percentage uncertainty means there's a small random error. And random error is basically experiments, like errors that are caused by like unknown and unpredictable changes in the experiment that's sort of not affected by the quality of experiment that's happening. And our second point would be that there's a pretty large percentage error in the experiment, which could mean there's a large systematic error. And systematic error is basically errors that's caused by the observer, or not the observer, the quality of apparatus itself, which can be fixed by either improving experimentation techniques or improving the instruments that are being used. And yeah, I think that's about it. Right, so moving on to question 5. It's a pretty long question actually. I'm gonna paste it in. Right here. Yeah. Right. So, question 1 says a student investigated how the type of acid in acid deposition affects limestone, a building material mainly composed of calcium carbonate. Here we see the solubility of calcium carbonate, and we see here that the student monitored the mass of 6 similarly sized pieces of limestone. 3 were placed in beakers containing 200 centimeters cubed of 0.1 mole per decimeter nitric acid, and the other 3 in 200 centimeter cubed of 0.1 mole decimeter sulfuric acid. See a nice little diagram here. The limestone was removed from the acid, washed, dried with a paper towel, and weighed every day at the same time, and then replaced in the beakers. The students plotted the mass of one of the pieces of limestone placed in nitric acid against time. You see a nice graph of the time in relation to the mass of the limestone in grams. Part A asks us to draw a line of best fit line on the graph. Now, one important keynote when you get a curved graph, what we can see is that a line of best fit doesn't have to always be straight. You know, in certain situations like of these unusual nature, we can draw a curved smooth line. So something along the lines of this, and that would still accurately represent the best fit line on the graph. Because it wouldn't make sense going something like this, because we'd miss like 90% of the points. So we can draw something along the lines of, keep in mind I'm operating on a mouse right now, so this is pretty difficult actually. Something the lines of this. Obviously it's going to be more smoother on paper. I'm using a mouse, so it's harder to operate. And yeah, that should be it for part A. It's a pretty easy 1 mark. Part B, I, says determine the initial rate of reaction of limestone with nitric acid from the graph. Show you're working on the graph and include the units of initial rate. Right, so what it means by initial rate of reaction is that the time has to equal to 0. So t has to equal 0. So we take this point right here. And in order to calculate the rate of reaction, we have the change in y over the change in x. So in order to draw or to accurately represent a graph when it's curved is to draw a tangent always. So right here we can draw a tangent on the line, which is going to be horribly accurated, which, yeah, that's a pretty good straight line. And here we can take the change in y, which is the y-axis, and then divide it by the change in x, which is the x-axis right here, which is the time. So here we have 4.48.08 minus 47.90 divided by 1 minus 0, which is just 1, which should equal to, we can calculate this properly, it should equal to 0. The calculator is a bit glitchy. It should calculate 0.18, which is the correct answer, I assume. And the units of the initial rate would be mass over the days, which would be 0.18 grams by inversely proportionate of day, because it's going down. So it's a negative correlation. And I'll just paste the remaining of the question right here. Remaining of B. And there's a C as well, yeah. So right here it says explain why the rate of reaction of limestone with nitric acid decreases and reaches 0 over the period of 5 days. So over the period of 5 days, why does the reaction decrease? Basically, that's what the question is asking. So it's 2 marks, so we need to make 2 points. So one of the points immediately that points out is that the acid is being used up. So since it's reacting the limestone with the nitric acid, as the acid is being used up, the rate of reaction obviously decreases. So you can say nitric acid is being used up, which also means it's the limiting reactant, which therefore leads to less frequent collisions, obviously. Anytime there's a question with 2 marks that you seem to struggle in, go on and write as less frequent collisions as your second point usually gets you the mark. For part 3 of section B, it says, suggest a source of error in the procedure, assuming no human errors occurred and the balance is accurate. So we're looking at random errors here, errors that are not affected by the quality of experiment. So we can assume that since the balance was accurate, we can use other variables, like possibly if we look at the diagram, we can see that the beakers, we can see that they were not covered, which could lead to evaporation occurring, which could affect the results in the procedure. So we can say beakers not concealed. Section C, part 1 says, the student hypothesized that sulfuric acid would cause a larger mass loss than nitric acid. So to look at this in a more chemistry way, we should write the formulas of sulfuric acid. So sulfuric acid is this, sulfuric acid, and nitric acid is, I think, HNO3. So to deal, or to assume that sulfuric acid would cause a larger mass loss than nitric acid, it's because sulfuric acid is actually diprotic, which means that it contains 2 H plus ions, whilst nitric acid is not diprotic, as it contains only 1. And because there's more H plus ions released, that means there's increasing reaction with the limestone because there's a higher concentration. So we can say here, since it's 1 point only, we can say sulfuric acid is diprotic. Whilst nitric acid contains only 1 H plus ion, which means I'm gonna go to the void area. So, which means more H plus ions react with the limestone, which cause a larger mass being lost compared to the nitric acid, right? So yeah, that's it. And for part 2 of section C, it says the student obtained the following total mass losses. So you can see in nitric acid with the samples, nitric acid loses it by 0.3 and then loses it by 0.1. And then sulfuric acid loses it by 0.3 and then by 0.1. So she concluded that nitric acid caused more mass loss than sulfuric acid, which did not support her hypothesis. Suggest an explanation for the data, assuming that no errors were made by the student. So I assume this has to be done from a mistake from the sulfuric acid side. So when calcium carbonate reacts with sulfuric acid, it produces calcium sulfate. So we can say that the calcium sulfate actually remained on the limestone instead of obviously dissolved into the beaker, which caused the mass of the limestone to be greater than what it should have been, because obviously, because it's reacting with sulfuric acid, it produces calcium sulfate, which is remains on the limestone instead of dissolving into the beaker, which could possibly be the explanation of why she got these results. Because obviously nitric acid is less reactive because it has less H plus ions, so it's more unlikely that it would obviously cause the same error as sulfuric acid. So we can just say that calcium sulfate, so CaSO4, remains on the limestone, therefore mass of the limestone does not change as accordingly. I don't know. Accordingly. I think it's an E or a G. Accordingly to the hypothesis. Because obviously this still matches the requirement of the question, because this isn't an error made by the student. This is sort of a random error. It's sort of a cause of chemistry, not a cause of the student. And yeah, I think that's it for this past paper. We've done all the questions. Thank you guys for watching. I hope this benefits you as much as it benefits me. And yeah, I'll be making more videos like this. See ya.